We consider the problem of cooperative learning, where networked agents sharing the common global minimum work cooperatively to optimize a global cost function, which takes the form of equation 1. We use the adapt and combine diffusion algorithm for cooperative learning, where each agent runs a SGD step using local data to optimize the local cost function, followed by a combination step that aggregates the neighbors' estimates. Cooperative learning improves the network learning performance. However, the aggregation step is vulnerable to besting attacks. If a normal agent assigns a non-zero weight to a besting neighbor and aggregates the besting values, then the besting agent can adversely impact the convergence of the normal agent. The problem of resilient consensus is highly related to our problem. In resilient consensus, it requires the aggregation result always lies in the convex hall of normal states, which is often referred to as the safety property. Although cooperative learning using distributed SGD in besting systems has been extensively studied, we found most of the aggregation rules fail to meet this safety property. Examples include the coordinate-wise median and geometric median in the right figure. If the adversary sends besting values that are small in each coordinate, it can make the aggregation results lie outside of the convex hall of the normal states. And at the next step of aggregation, agents will adapt their states on the basis of the wrong aggregation result, and finally they may converge to a point desired by the adversary. From the previous example, we found it's necessary to guarantee the safety property for cooperative learning to cope with besting attacks. We formulate our problem as follows. First, we want to design an aggregation rule such that the aggregated result by a normal agent is always inside the convex hall of its normal neighbor's states, even when the agents cannot distinguish between normal and besting neighbors. And then we want to show the diffusion algorithm using this aggregation rule achieves resilient convergence for every normal agent. We utilize the notion of center point to guarantee the resilient aggregation. Center point is a point such that any closed half-space that contains this point must contain at least n over d plus 1 points from the total point set. For example, in 2 dimensions and for 6 points, any closed half-space contains a center point also contains at least 2 points, that is 1/3 of the 6 points. One can think of center point as a generalization of median in higher dimensions, and it is guaranteed that a center point always exists and is not unique. We find center point satisfy the safety property as long as the number of besting neighbors is less than n over d plus 1, where n is the number of the total neighbors. See this example. The star is a center point that always lies in the convex hall of normal nodes, regardless of the selection of the besting node, if there are at most one besting agent in the network. And the yellow polygon constitutes the safe region such that any point in this region is a center point. Using center point for aggregation, we can further guarantee the resilient convergence of the diffusion algorithms, and the network learning performance is guaranteed to be better than the non-cooperative SGD algorithm. In 2 and 3 dimensions, computing a center point takes linear and quadratic time respectively, and in higher dimensions, computing an exact center point is expensive, but we can use approximate algorithms to compute an approximate center point to reduce the time complexity. We evaluate our method using a cooperative mobile adaptive network, where agents aim to estimate and move towards the target's location using streaming sensor data. We found under no attack, diffusion with all the aggregation rules as well as the non-cooperative SGD converge to the target. But with 6 besting agents, only the centerpoint-based diffusion algorithm converges to the target, and its mean square deviation is better than the non-cooperative SGD. Finally, we obtained the same experimental results using real robots on the multi-robot testbed robot room developed by Georgia Tech.